Bonjour, je suis David Woodhouse et je regrette je ne parle pas français. So I will speak in English. I'm going to talk about flash memory, how it works, what it is internally, what makes it special and interesting to deal with, and how we deal with those problems in software. Okay, so yes, that's the basic rundown of what I'm going to talk about. I'm going to talk about flash translation layers which use flash to pretend to be a disk. Basically, we have this pretense that we are spinning Rust, which is something that came about in the very early days of using flash storage because we had to plug into a PC which had the Int13 disk BIOS services that represented a disk, and there was no simple way of presenting a native file system. So we had to pretend to be a disk for the benefit of DOS. And unfortunately, we're still suffering this pretense decades later. But I will also talk about other approaches for using file systems directly on flash. So this is a flash cell. It's very much like a transistor. When there is a voltage on the control gate, current can flow between the two sides of the transistor. The difference in flash is that there is an isolated floating gate between the control gate and the substrate of the transistor. And when this is charged, it affects the electrical field applied by the control gate. So basically, the difference between a flash cell that is programmed to 1 and a flash cell that is programmed to 0 is the presence of electrons in this gate. And so the voltage you have to put onto the control gate to allow current to flow varies, and that's how you read the contents of the flash. And you charge it. I've forgotten the precise details, but you charge it by putting a high voltage on one of the lines to actually force electrons to jump into the floating gate, so that the programming of the flash and the erasing is done with high voltages across it. Right. Okay, so this is how we lay out flash cells in NOR flash. This is the early types of flash. And basically, any individual cell can bring down the bit line. So we only have to apply the voltage to the control gate of the one flash cell that we're actually trying to read. But it's a very inefficient layout. You can't get flash chips as dense as you can with NAND flash. This is what NAND flash looks like. So you see it can be packed a whole lot more densely onto the silicon. And what you have to do to read a given cell of NAND flash is to apply a sufficient voltage to all the other cells in the line to make sure that they will pass current, whether they're programmed or not, and then you apply the smaller voltage to the cell that you're trying to read, and that way you read out just the bit that you're interested in. But you are messing with all the other cells, adjacent cells in the line, every time you read a bit. So that's one string of NAND flash. And then, of course, one bit at a time isn't useful, so we build them up into arrays blocks. And we have multiple pages in an arrays block. So an arrays block may typically be 16 kilobytes, made up of pages of 2 kilobytes with an extra few bytes. Because of the unreliability of NAND flash, we have a few extra bytes for error correction. So a 2K page flash is actually 2112 bytes generally to give us space for the error correction. And so when you're accessing NAND flash, you will write or read a page at a time, which is one of the columns in this diagram, and all the other pages are irrelevant. So I mentioned that flash is unreliable, and these are some of the reasons. The charge in the floating gate can simply escape over time. And also, as you're forcing electrons to tunnel into the floating gate and discharging it, leaving them out, you also find that over time a charge builds up in the insulator that's around the gates, the part of the transistor that's not supposed to be conducting. And so that is actually what destroys the hardware over time. That's why they die, because the charge is built up in the insulator and the structure has basically broken down. And there are also two things that happen while you're using it, write disturb and read disturb, which you may well have heard about, but I'm going to explain exactly how those happen.
In practice, it is losing information in a matter of weeks or decades.
In which way? Probably, yeah, months, years. But if you're just talking about leakage from flash cells over time, when you're not doing anything to the flash, then it takes some time for that to happen. And for the charge to build up in the insulator, that only really happens, or that mostly happens when you're erasing a cell. And so that's why the lifetime of flash chips is measured in erasers rather than years, months, etc. So, and read disturb and write disturb, you might be able to guess happen, when you read or when you write. So it's difficult to answer in terms of weeks or months because it depends how you're using the flash. And one of the big things that we have to do when we're managing flash in software is manage how we use it, reduce the number of erasers we do, reduce the number of writes we do. That's one of the big things that we have to do when we're managing flash in software. So this is how you program a cell. So when the flash is erased, all bits are set to 1, and when you program a page at a time. So this is the layout that I showed you before. For the pages we're not interested in, I mean the voltages are fairly random, but it's something like this. So the pages we're not interested in, we put an intermediate voltage, 10 volts on those page lines. And for the page we're programming, on that column we put a higher voltage. And then for those bits which we want to program, the bit line goes to 0, so that across the cell that we're trying to program, that we're trying to force the electrons to jump into that floating gate, there is that higher 20-volt differential. And everything else has either no differential or a small difference. And so that's how we program the individual cells in that array. But that also explains the write disturb, because those cells which have the smaller differential that's not supposed to be enough to program it, there is still some chance there of causing essentially a bit flip in those cells. So that's what write disturb is. So when you're programming one page in the NAND flash, you will actually have an effect on the surrounding pages, and you may disturb the content of those pages. Excuse me. So I just have the notes there on come on, that one. Right, so the write disturb, I have notes here that it's 1 in 10 to the 10, so 10 milliard for single level cell flash, and 1 in 10 to the 8, so 1 in 100 million for multi-level cell flash. That's the incidence of write disturb.
And is it improving with technology? Because you have told
No, it's getting worse. Well, we like to make flash bigger and smaller, and what's going to happen? It's going to be easier to get the disturb. We're going to multi-level cell, which I'll explain in a minute. But yeah, it's just getting worse. hardware guys say, oh, well, they'll fix it in software. It's fun. So read disturb is, yeah, basically the same thing. You put the, as I said earlier, when I displayed just a single string, you put a sufficient voltage on the bits that you're not interested in so that they will always allow current to pass, and that is going to cause disturb of the contents. And this is more common. This is 1 in 10 to the 6 for SLC and 1 in 10 to the 5 for MLC flash. So that's even more scary, isn't it? The simple fact of reading one page in a flash has a 1 in 100,000 chance of affecting a bit in one of the adjacent pages. So I've spoken a little bit about SLC and MLC. So this is a basic single level cell. It contains a 0 or a 1. And basically, if it passes current when you put a small voltage on it, and it's typically in this range, then it's at 1. It's not been programmed, basically. It's been erased to a 1. And if it's been charged, and if you need a higher voltage to make it pass current, that shows you that it has been programmed, and that reads out as a 0. That's a single level cell. But in a multi-level cell, you actually have 4 levels of charge. And yes, you can pack twice as many bits into a single cell, but of course it's a whole lot less reliable because of the there's much less information, less distance, much less leakage has to happen before the contents of the cell have effectively changed. So that's why MLC is very attractive, because it's much more dense. You can get twice as much data into it, but it's also much less reliable, which is why you see the enterprise SSDs often will be using SLC, and that's why they do it. The expensive ones will be using SLC flash. And obviously this is a 2-level cell. People have been talking about going to 8 bits, 3-level cells, 3 bits of information, and dealing with the resultant interesting behavior. So that's basically how flash works internally. This is the interface it tends to give to the outside world. Unlike NOR flash, which was basically wired up as a ROM, you had a data, a byte word of data lines and any number of address lines to cover the entire range of addresses within the flash. NAND is done slightly differently. It has a data bus which is used for multiplexing in both the addresses you want to access and the data and commands for erase, etc. So with simple protocol for address latch enable, command latch enable, basically you put the address, the relevant byte of the address, or the command onto the data lines and toggle the appropriate line, and then it will go off and do its thing. If it needs to read, it will tell you when it's ready, and then you read the data out, etc. So it's very simple electrical interface, and it's usually very simple to replace one chip with another because they all have the same interface. If you put a larger chip in, you don't have to suddenly find extra address lines from somewhere and wire up extra pins to it. So it's relatively simple to change chips, to probe the chip and to discover what it is. I should be going forwards, not backwards. So these are the issues we have to deal with when coping with flash. Obviously, we have to do error correction. We have the extra space in each page to store additional data for error correction syndrome. We have to deal with bad blocks because some blocks will have gone permanently bad with leakage into the insulator, or may have been that way from the start. So we have to map around bad blocks, and we have to detect them as they go wrong. We have to program pages sequentially. So within a given erase block, we are told that we must start at the first page and program that, and then the next one, and then the next one. We mustn't do random access within that erase block. Now, that's not really, as I understand it, a fundamental property of the hardware. I think it's just that that is the best way to avoid write disturb as we're programming. And so it is mandated in the data sheets that we access the flash that way. And we need to do garbage collection. Because we can only erase a full erase block at a time, we may get to a point where almost every erase block on the flash has been used, but every erase block only contains a small amount of data that we still actually care about. So imagine a huge flash with all of these 16K erase blocks, of which we only care about one 512 byte, one 2K page within each block. We have to consolidate that somehow. But basically what that means is we have to copy the data that we still care about from, pick a victim block that needs to be erased, copy the data that we still care about from that block to another block that we can still write to, and then erase the original. And by doing so, we effectively gain free space, because the pages that had been written to that no longer contain valid data, we can now write to them again because we've erased that erase block. So the garbage collection involves moving data around on the flash, which of course means more erasers, more writes. So even when you're not actively writing to the flash, the management may have to do so anyway. And we need to do wear leveling as well. When we're doing this garbage collection or any kind of write, we actually want to use the flash evenly across the whole of the physical flash. We want to move things around because if we concentrate on just a few sectors, if you imagine an embedded device, when we were first doing this kind of thing in Linux, we had embedded devices with maybe 16 megabytes of flash, of which maybe 10, 12, 14 would be your kernel and your libraries and programs that almost never changes. Say 12 meg of that, 2 megabytes of volatile data that does keep changing, and 2 megabytes of space. And what you don't want to do is leave your 16 megabytes of flash completely untouched with your data that never changes, and wear out the remaining 4 meg of physical flash so that it's completely dead before you've even done any erasers on the rest of the flash, because the lifetime of your device will be much shorter than if you occasionally, when you're garbage collecting, pick a block that didn't need to be garbage collected, it's completely clean, copy its contents somewhere else, and then effectively put that physical block into the pool that's being used. So garbage collection will not only pick for victims that, the blocks which have lots of dirty data, obsolete data, but sometimes your garbage collection needs to pick clean blocks because you need to do wear leveling. And in some of the newer devices, we also have issues with paired pages. Effectively, it's one, I don't know why they didn't just do it as telling us the page size doubled. But basically, you have to deal with two different pages together. And if you write to one, you must write to the other. But being hardware people, they like to make life interesting for us. These pages aren't always even adjacent. So it's not just if you write this page, you also have to write the next one at the same time. You can pretend the pages are twice the size they are. Sometimes it's pages 0 and 3 are paired, and pages 1 and 2 are paired. So effectively, if you want to do something simple, you have to imagine that the page size is 4 times, and you have to write all 4 pages at once. Or, play tricks with interleaving. So there are a lot of interesting problems we have when dealing with Flash.
On the USB key, which of these are done on the key set and which are done outside?
There's the third possibility, which are not done at all. You did say USB key, right? Error correction will be done. Well, basically, the USB key is pretending to be disk. It is pretending to be spinning Rust. So you cannot rely on the operating system, the file system, to do anything. So anything that gets done is internally. The USB key will have essentially it has a file system internally, and I'm about to talk about how they work, or how they can work, some examples. And it should do all of these. Often they don't. Often they do them really badly. But it's a black box. You can't see it. You can't see what it's doing. The only way we have to know exactly what a given USB key is doing, or SD card, whatever, is to take it apart and put a logic analyzer on it and watch what it's doing. And we have some horror stories from doing that. So we actually did this with an SD card, and we watched its garbage collection. So I spoke of garbage collection, and I said, you pick a victim block to erase, you copy its contents and write those contents elsewhere, and then you erase the victim block. There was an ordering implicit in what I said. Then you erase the victim block. So we found a device which will pick a victim block to be erased, copy its contents into RAM, and then erase it. And then, not content with this, it will take a second block, copy that block into the original erased block, erase the second block, I think this must have been for wear leveling, and then finally copy the original contents back from RAM into the second physical erase block. I have no idea what the people who did this were smoking. But, yeah, you end up with these devices that pretend to be a disk. They have a file system internally, which is written by the same crack-smoking hobos they drag in off the street to write PC BIOSes. And it's a black box. You can't see what it's doing. You can't do a file system check on its internal structures when it goes wrong. When it goes wrong, it just breaks. How many people in here have got a USB stick that has just broken and stopped responding at some point? Yeah, that's the problem with the SSD approach, is that it is usually a black box that you can do nothing with. That's one of the problems. But no, I'll talk a little bit about how an SSD might work. So this is vaguely based on one of the early examples, the disk on chip, which was quite common in the 90s, in fact. And it used to have, you'd start off with a physical erase block would represent some equivalent size of the virtual disk. It wasn't a one-to-one mapping of one physical erase block to another. But a physical erase block, there would be some metadata which said which virtual erase block it represented. And inside there were sectors, which are the individual pages. This was in the days of Flash with 512-byte pages, which make life slightly easier, because that could represent a 512-byte disk sector. So imagine only the first two sectors of this virtual erase block have been written. That's fine. We write those. The rest is blank, can be written later. This actually even predates the rule that you must write pages sequentially. So at this point, you could write pages out of order. So then the operating system comes along and says, right, I want to overwrite the first four sectors. Well, overwrite the first two and write new date, the first data you've seen for the sectors 3 and 4. So what happens is we made a chain of physical erase blocks which all represented that same virtual range of disk. And so we just had sufficient metadata. We used the spare area in each page for this to say that actually the contents of sectors 1 and 2 come from this second block in the chain, and the contents of sectors 3 and 4 come from the first block. So we build up a chain of erase blocks for a chain of physical erase blocks for a given virtual erase block, and then here's another write, extending the chain even further. And obviously, this can't go on forever. At some point, you have to do your garbage collection and fold everything back into a single erase block, and that's simple enough to do. You just copy them, and then the older blocks in the chain can be erased, right? But this basically shows write amplification, where you've only done a certain number of writes to the flash from the operating system, but in fact more writes, more data copies, more erasers have gone on in the background without you really knowing about it. And one of the other issues, so this is yes, we erased the previous blocks in the chain after doing the folding. So one of the other issues with this write amplification is actually you end up copying data that the operating system doesn't care about. Because the USB stick, whatever, the SSD, is a black box, the operating system can't see into it, but the black box can't see what the operating system is doing either. So you might have your file system and fill it up with files, use every sector on the disk, and then delete them all. But the disk doesn't know that. The disk just has sectors. And these sectors have data in, which it will faithfully preserve and copy and garbage collect from one sector to another, even though you don't care about those sectors at all. So that was one of the biggest problems with the pretending to be a disk approach. And that's addressed by the trim or discard operation, which is being added to ATA and SCSI standards and being added to decent SSDs. So basically, going back to one of the intermediate stages in the diagram I just showed earlier, the operating system can say, I no longer care about the contents of sectors 1, 2, and 3. Just forget them. And then when the chain is folded, in this case, it hasn't actually prevented any erasers from happening, but you can see how it would. If you now want to write new data to those sectors that have been trimmed, they can go in those slots there. You don't have to add a new block to the chain as you would have done in the previous dot diagram. So that's one fairly early translation layer. That's just an example of how it can work. That, they don't all work like that. Another one could be very much log structured. So, this is perhaps a more modern one, deals with the fact that you can only write pages sequentially with an erase block within an erase block. And you start off writing sectors. We'll do the same write pattern as before. First, you wrote sector 1 and 2, and then the operating system writes sectors 1, 2, and 3, and 4, so we just write them down. It's basically a log. And this is quite a popular mode of operation. It makes writes nice and fast. Writing to flash is relatively slow in terms of the hardware, but at least it can be sequential, and you can just throw the data at the flash. So it does mean that reads are slow, but of course it's not actually a disk, so you don't have to worry about the head moving all over the place when you seek. But it does mean that there's a cost in terms of finding where all the data are. When you turn the SSD on, if it's using this type of translation layer, it's actually got to go and find all the sectors. And you'll find that something doing this kind of thing will have a huge amount of internal RAM to keep a big table of where sectors are, and it will take a fair amount of time to power up as well. So one of the other new things that's being added to the ATA spec is a device sleep functionality for power management, because if you're doing this kind of thing, you really don't want to just turn the disk off and turn it back on again. You want the disk, its internal controller, effectively to suspend to RAM. So it's got all this big table of where to find all the sectors in RAM. It can put that RAM into auto-refresh and switch everything else off. And that's why we now have the device sleep facility for SATA devices. It allows this kind of thing to work effectively.
This also means that the FBI will always be able to find my data, even at the kernel level I have with it out.
Yes. Well, possibly some of it. And yes, assuming they have access to the internals, yes. Some of the SSDs will actually do encryption internally, and there is a secure erase facility which basically just throws away the key. And in that case, you don't have that problem if you trust the device manufacturer. Because the data are all there, but they're all encrypted with a key that no longer exists. So that there are ways of handling secure arrays, but yes, in the general case, if you had files on it's just an extension of the same problem, right? If you unlink a file from the file system, forensics can find it. You have to overwrite the same sectors of the disk, And this just extends that one layer further down, that when you overwrite those same virtual sectors, actually even that doesn't mean anything. You've got to ensure that the physical erased blocks are erased. So yes, that is an issue, but it is addressed by some of the high-level, the high-spec SSDs, which will use encryption internally, because basically the encryption is free. The time that's taken is to get the data in and out of the flash and to move it over the SATA bus. To encrypt it in transit it just doesn't hurt. Well, that depends on what the disk does on being told to trim. It might do nothing. If I go back to that, no. If I go back to that example of using trim, it doesn't actually delete anything at this point. If we're told to trim sectors 1 and 3 there, we don't care about their contents anymore, but we haven't folded that array, that chain. We haven't physically deleted the data. And the trim is defined in the spec as being optional. It is not a secure arrays. It is explicitly not a secure arrays. It is a hint to the file system in the device, a hint to the black box to say we no longer care about the contents of these sectors, but it is not guaranteed that the data will be removed, and you wouldn't want it to be. This is to fix the problem of the inappropriate layering, but it doesn't guarantee a secure arrays. I don't think it would even be sensible for a device to offer that as an option in trim. There are separate commands for secure arrays. So where was I? I think it's 11 o'clock. I should finish, but I started late, so I'll keep going until people start walking out. There we are. So this is the SSD approach. It's basically your file system, your traditional exe2 whatever file system, on top of another file system. And it's hard to optimize. You'll see some USB sticks only do proper wear leveling on the first section of their disk. They divide a large sort of multi-gigabyte USB stick up into multiple regions which are effectively managed separately. So it's an internal translation layer for different regions within the flash. And sometimes they only do wear leveling within each region. So you might find that if you put a fat file system on a device like that, you wear out the first region much faster than the rest. They don't do wear leveling across the whole device. They only do it within that region. But they expect you to use fat on it, so maybe they only do wear leveling properly there, or they do some clever trick to optimize for wear leveling in the first region of the disk. But if you put ext3, ext4 on it with a journal which is not in that first region of the disk, you're screwed. We've seen devices which were clever and tried to do trim for themselves, assuming that you have fat laid out as a Microsoft operating system would format it. So it knows exactly where the fat is. And when you mark a cluster as free in what it thinks is the fat, it then goes and forgets the contents of what would be the equivalent cluster on the disk if you were actually using fat. So, yeah, it's all kinds of interesting things have happened with SSDs. But there's also missed opportunity for garbage collection. Basically, when you're copying data around, the file system, the higher level file system, can have a better idea about what data are volatile and are going to be overwritten soon, and what data are long-term data that will never get changed. And there are opportunities for defragmenting and sort of collecting data back together as you garbage collect, which a native Flash file system can do and can basically optimize its own storage. Whereas if you have this separation and a device pretending to be a disk, you don't get that opportunity to improve the layout as you garbage collect. And the other thing is with transactions. So you have a POSIX file system will give certain guarantees about atomicity. So a rename of one file over another one shall be atomic, and that's why everything will work by writing out a new file in replacement and overwriting. But that's another write amplification that we don't necessarily want on Flash, writing out a new copy of a file and completely overwriting the old data. We can do transactional-based file systems, but it's a whole lot easier to do that directly on the Flash if you haven't got this artificial layer of pretending to be a disk with its own atomic 512-byte sector overwrite, which is the interface that disks offer us. So the number of issues with the approach, I said earlier why it came about, because that's what DOS understood. But it's no reason why we should continue to deal with the limitations of MS-DOS. But there are reliability issues as well. None of these are fundamental. It doesn't have to be unreliable. It just is. It's a closed source file system in a black box device that you cannot see, you cannot debug, you cannot even recover when it goes wrong. And as I say, implemented usually by crack smoking hobos, they drag it off the street. It's just done badly, and it's because people don't care. People know that USB sticks, that kind of thing, is not reliable. They know that an SD card is good for getting your photos out of your camera and putting into your laptop, but if you try and store your dissertation on it and then end up crying because 3 years of work have been lost, nobody's going to have any sympathy for you. People know that, so there is no expectation, no pushback from customers to make things more reliable. Thankfully, that is changing as we're seeing this kind of technology, not just in disposable devices, but also in SSDs, in laptops. People start to care just a little bit more when it's in their laptop. So we are seeing big improvements with SSD technology. So the reliability is getting there, but there are still some of the fundamental issues with it just being the wrong approach. One of the other issues we had with USB sticks was alignment, and you have to take special care with some of them to align your partitions on your disk with the physical erase blocks, because you don't want a partition that starts halfway through an erase block, and you don't want your clusters or your allocation unit to be overlapping erase blocks. That's going to be massively inefficient. But we don't actually know where the erase blocks are, and sometimes they offset them just to make sure it would line up nicely for FAT. We have all kinds of interesting fun, and the worst thing about it is you just can't tell. So we have support for dealing with Flash directly in Linux. We have synchronous read and write calls, just function calls you call to read and write a section of the Flash. Erase is asynchronous because it takes longer, so you kick off the erase and then you'll get a callback later when it's completed. We have software error correction libraries to do everything for you, so that basically you can just worry about the data and the ECC will happen. Often on decent hardware we'll have DMA support and error correction in hardware, or at least generating of the error correction syndrome on writes and detection of errors on reads, even if an error is just signaled to you and then you have to do the complicated mathematics to fix the error. At least the fast path is, well, fast. And bad bot management, so the the Linux the Linux code supports a number of schemes for remembering which blocks are bad by keeping a table of bad blocks, etc., and so that users of Flash in Linux don't have to use that. Basically, the way that we advise to use Flash these days is UBI. It's designed, mostly came out of teams working in IBM and Nokia, and it's kind of LVM on steroids mostly for NAND Flash, but it works on NOR as well. It gives you static volumes, so essentially files which are useful for bootloader, kernel, etc. These can be atomically overwritten, so you can update your kernel atomically if you so desire. You can also have backups so that you can fall back to the last one that does actually boot. It does the wear leveling internally. It does a CRC protection on the whole of the image so that, again, it can fall back to a previous image if the CRC fails when loading an image. But it also gives you dynamic volumes, which are writable. It gives you basically a simple mapping from a logical erase block within your volume to some physical erase block somewhere, and you don't necessarily have to care. You tell it to erase the virtual block, and it will actually defer that erase, do it some other time. Basically, it just unmaps it. It's almost like a trim was. It's enough. UBI gives us enough of what the SSD does. So it does some of the useful things, but without that artificial barrier and that layering that we don't really want. It doesn't get in the way. It basically gives us enough to implement decent file systems and things on top of it. So we have UBFS to run on top of that. We've also been talking about making ButterFS work. ButterFS has a nice storage abstraction which allows it to do its RAID, RAID 5, etc., and work on multiple devices. And this can be extended to work on UBI as well. ButterFS work is quite nice because it has this copy on write mode of operation. It doesn't overwrite data in place, which is the important thing that you cannot do on Flash. So ButterFS on UBI should actually work quite nicely. I've been talking about implementing this for some time, but I will get around to it eventually. And the other thing that UBI does is scrubbing. Because of read disturb and write disturb, you actually need to go back and read pages, physical pages, even if you don't care about their contents. You need to see if there's been a bit flip. Because you have error correction that can cope with a certain number of bit flips before it just throws its hands up in horror and says, your data are corrupted. So what you need to do is go through the data and read it, notice that 1 or 2 bit flips which are still correctable have happened, and garbage collect that immediately while you can still recover the data. So yeah, an ideal hardware wish list. Yeah, don't give me an SSD. If you're going to give me a device, embedded device with Flash for storage, I don't want to see an SSD. I don't want to see SD, MMC. I want real access to Flash, fast DMA, error correction in hardware, and scrubbing as well. So when I need to do scrubbing, I don't actually want to see the data. I just want the Flash controller suck the data in, pass it through the error correction hardware and say, yeah, that's fine. I don't want the data coming over the bus to me. And I want a page copy integrated with the error correction. A lot of Flash chips do have a page copy operation, but it's useless because it will copy the data, errors and all, which isn't very helpful. What I actually want to do is copy the data out, pass it through error correction, or at least validate it, and then write it elsewhere for garbage collection. But again, I don't necessarily want that to come into host RAM. As long as it's corrected, it's fine to have that internally. So that's what we're starting to see from some of the decent NAND flash controllers. Another thing that would be really nice is erase counters in hardware, so that you don't have to manually keep track of how often each physical erase block has been erased. If you could simply query it and ask for that, or if not an actual counter, then some measure. In fact, the you can tell quite well by the amount of time it takes to erase in a raised block, and if it would report that coherently, an average of the erase time for the last few erases of a block, that would be a good measure of the wear, would allow us to improve wear leveling. So with that, I think I'm about a quarter of an hour over my time. Sorry? Okay. So, any questions?
The full picture, does it improve over time or not? I mean, can we expect as a user better devices, better protocols to them or not?
So better protocols to...
Would my SSD disk I'm buying Wimo Gene, the cheap Asiatic speed you have, in 2 years better than today?
Yes, SSDs are improving a lot, and not only are they improving internally with just better quality internal firmware, because, as I say, people are putting them in situations where they care more about data integrity, but we're also improving the protocols. There's work going on in the sort of T10, T13 standards organizations to improve the SATA, the SCSI specs. I talked about trim, I talked about device sleep. These are things which are introduced into the ATA protocol specifically to allow SSDs to get better. So yes, absolutely, they are getting better, they are getting faster. I said very early on that as we go to MLC, basically the physical hardware of the flash storage gets worse, but we just do more in software to cope with that. So yes, they are getting bigger, they are getting better, they're getting faster, they are getting more reliable. But still, I think we can do a lot better with full access to it in software. I think we can get quicker, we can get more reliable much faster if we have access to this in software. So I wouldn't necessarily advocate raw NAND access in a laptop type device. The SSDs are fine for that. But for embedded devices where you are not going to put an Intel Enterprise SSD in there as storage, where you're going to use an MMC card or something, then you really ought to be looking at real NAND and a real flash file system, because that's where it's going to make a lot of difference.
Today, if I'm buying an SSD, I will naturally install maybe XT4 or XFS or whatever. I have tons of choice to put my file system on it. If I take a real NAND flash, I roughly have the choice of GFFS2. Do I have other choices?
UBFS. I wouldn't necessarily recommend GFFS2 for bigger devices these days. GFFS2 I wrote about 10, 11 years ago in the days of 16 meg of NOR flash. We retrofitted NAND flash support to it with a write buffer. GFFS2 was purely log structured. As something comes in, you write out this changed, this changed, this changed. Mounting it was slow because, I talked about this with a log structured FTL earlier, because it had to go and work out everything. And yeah, we added the write buffer so that it would batch things into page-sized writes to cope with NAND flash, and we added some better handling of error correction and dealing with failed writes specifically for NAND flash, but that was retrofitted. In the days of the One Laptop Per Child project, we had 1 gigabyte of NAND flash on the early $100 laptops. We did a lot of work then on improving mount time and putting in essentially checkpoints, and that made things a lot better. We had a structure at the end of every erase block which basically described what was in that erase block, so that rather than having to read the whole flash, you could only read the checkpoint at the end of block. And we did a lot of work on data structures, and we made it acceptable on 1 gigabyte of flash. And it would take, I think we got it down to maybe 2 or 3 seconds to mount 1 gigabyte of NAND flash. But that was tolerable, but it's not something I would design for these days, especially if you're going to multiple gigabytes. These days, I mostly consider GFFS2 to be obsolete. In that kind of situation, use UBFS. UBFS is designed specifically to work with NAND, to work with bigger file systems. It actually has structure on the file system. It doesn't just have this big log. So, yeah, Jervis 2 is great for smaller devices, especially for NOR, but also, you know, we made it work on NAND. But I wouldn't be advocating it, even at a gigabyte. Even, you know, I was even looking at OLPC, moving OLPC to UBFS, but UBFS was quite new in those days. But these days, yeah, we have UBFS working on the LPC laptops.
When does UBFS got released?
Some years ago, 2-3 years ago. It's quite mature. People have been using it for some time. IBM have been using UBI, which provides all the underlying sort of wear leveling and other things in their service processors for their big iron mainframes for a number of years. They were involved very early. UBI came before UBFS, which might be obvious, but the file system on top of it came almost as an afterthought, and Nokia did a lot of work on that.
Yes, I have another question. How about NVM Express? Isn't it better than ATA for laptop SSDs?
It tries to address some of the issues. I mean, it gives you a faster data path, and it's slightly better designed for dealing with flash. So, for ATA, we've had to go and retrofit the trim and device sleep and other things, and those have all been built in. We've known about those requirements from the beginning of NVMe, but essentially they're coming together. It's a new. It is as ATA, SATA was to IDE. It doesn't fundamentally change anything. Yes, it's nice and shiny and fast, but that's about it. Yeah.
Okay, so we'll stop. One more question? Quick, very quick.
I was wondering how the metadata on the flash is stored. For instance, on MLC flash, we heard that the cells are very weak or fragile. Is the metadata using SLC cells or NOR cells? My fear is that the flash can be weakened only by the metadata. Maybe sometimes the data are still there, but the metadata are dead.
Often the case. Which devices were you talking about? Anything?
Any type of flash.
It can be done. There are some devices which have a combination of SLC and MLC, and they try and set it up so that metadata goes into SLC and data goes into MLC. But how? It's a black box. That's a really hard problem to solve, unless, again, you let the operating system know what's going on. So that would be a lovely approach, but it's really hard to get it right. Yes, I think there has been some attempt to expose that in NVMe, but I don't think it's feasible in SATA.
So there are still 2 questions, I think. And this will be released the latest one.
Okay, my question is, how do you see the future of embedded devices with regard to MLC flash? Do you think that in 5 years from now, embedded device will still be using raw access to MLC flash, considering the higher ECC power required to handle MLC devices, and also all the problems you mentioned, page pairing, maybe the need to crawl the device to avoid data loss and stuff like that. So I see people turning more and more to eMMC or managed NAND. And if you look at Android, also the Android system is turning to XT4 file system on eMMC.
Yep.
So how do you see the future of raw MLC for Linux in 5 years from now? Say?
There are a bunch of devices still using it. Yes, you're right. There is a move towards using eMMC, ESD. I'm going to wait and see how that turns out. There are issues with that. We may find that the manufacturers of those devices actually improve and they become more reliable. They haven't yet. There are still numerous horror stories about those devices. I've been talking to some of the people working in automotive devices about, it's horrible. But people are bringing out new system-on-chip devices with NAND flash controllers, decent NAND flash controllers. I gave you a kind of a wish list there, which solves a number of the issues you were talking about, right? If you have a controller that can do the ECC in hardware, if you have a controller that helps you do the scrubbing, that helps you work around the issues that
But you mean inside an NAND flash or inside your controller?
inside the controller.
Because what I see with the recent NAND devices, when I talk to manufacturers, is that the number of bit flips that you need to correct is rising so fast that ASICs and SOCs just can't cope and follow the trend.
So how does an SSD do it?
Sorry?
But if you have an MMC card, it's still got to be done somewhere.
Yeah, sure.
Where?
In the controller, I guess.
Right, so it's the same
in
place. So it's sometimes even the same controllers. If you look at some of the, I think the Intel Moorestown boards, they had a Denali controller, which was basically some IP brought in from somewhere, which is also used in SSD type devices. It's the same controllers. It's the same block that has to, they have to have the ECC somewhere. Even if it ends up on the die with a NAND chip, it's still the same. Somebody's got to implement that amount of error correction in hardware. It's just a question of where you put it. And
My point was I was seeing this more in the device rather than in the controller in the future.
Yes, there is some move. Yeah, with the managed NAND, there is some move towards that, and that helps. I mean, it would be really lovely to see a hardware interface, whether it be the chip itself or whether it be chip plus controller. To be honest, that's an artificial distinction. That's only whether the controller is inside the package or outside, right? I would love to see something that doesn't do the whole pretend to be a disk, but just offers the same kind of functionality that Ubi offers you. So it gives you static volumes, or at least the dynamic volumes, and the virtual to physical erase block mapping, the scrubbing, the basic operation, deal with the interesting issues of flash, but not the whole pretend to be spinning rush. That's the ideal hardware interface that I'd like to see. And we could do it with SSDs these days. You change the firmware, you can have something that doesn't do all the complex stuff, that just gives you an Ubi-like interface. That would be beautiful.
Bien, merci beaucoup, David. Thanks a lot.